We have studied so far how half band filters and Nyquist M filters can be designed. So, with this in mind, we can get into some system level properties. These things are these properties are going to be helpful for us when we deal with filter banks, and the goal is if you want the overall distortion function, and we saw when we derived the general form for the M channel filter bank, we said the overall, if you remove all the alias components, the overall filter transfer function, distortion function would be the first component A naught of z, which is your unaliased component, right. I mean if you remove all, if you set all the aliasing components to 0, then the overall distortion function using your analysis filters and your synthesis filters would be the unaliased part. Now, our goal is, if you want that transfer function to satisfy certain properties, such as the perfect reconstruction property, which is this transfer function has to be just some delay with a gain. Can we define such can we realize such filters, right. And in the special case, when the delay happens to be 0, no delay essentially, right, no delay but just a gain, then you can think about it in this form where they are like Nyquist M filters, but possibly realizable through some spectral factorization, right. So, we will study some of these properties. So, the first property is strictly complementary functions. This is also called a C property. So, H naught of z, H1 of z dot 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 H m minus 1 of z are strictly complementary if their responses add to a delay. That means summa k equals 0 to m minus 1 hk of z is some c z power minus n naught. Recall, I just put the subscript k here, unlike in the Nyquist M case where the k was folded in here into the argument with omega power k, z omega power k, right. I just put a subscript k here because it could be generally any filter, any band pass filter, right. If this satisfies such that c is not equal to 0, of course this is trivial condition, then they are called strictly complementary filters. So, for m equals 2 case with c equals 1 and n naught is n upon 2, right. If we start with our base filter, H naught of e j omega is some e power j omega n by 2 times some h r of omega, then I can say H1 of z is say z power minus n upon 2, because I minus H naught of z is what I have, right. So, now I can say that H1 of e j omega is basically e power minus j omega n upon 2 times 1 minus h r of omega. Because h naught plus h1 should just add up to a delay with a gain of 1. Right. If you think about how this could be sketched, so this is case m equals 2 with c equals 1 and n naught equals n upon 2, right. If you think about equiripple filters, and this could be your pi by 2 frequency. This is your h naught and this is your h1 of E j omega, right. So, therefore, the sum would ideally have to be 1, but you could have oscillations around 1, this could be 1 plus delta 1 and this could be 1 minus delta 1. Similarly, you could have a delta 2 and minus delta 2 symmetrically. I mean, this is just, I have not written the magnitude. If I write the modulus and if I square it, of course, you will not see the negative down, right, you will not see the negative ripple down. So, in general, you can think about that for strictly complementary functions, the sum of the filter responses should add up to a delay with a scale factor of c, and in the special case when m equals 2, right, and if you choose such that c equals 1, the gain is 1, with some preset delay, it boils down to what we are familiar with the quadrature kind of case, right. At pi by 2 basically there is an overlap, they intersect. The next special function or special property for filter banks is the power complementary functions. So, if you are given filters h naught, h1, h2, so on till h m minus 1, they form a power complementary pair if you look at the magnitude square responses over all the m filters, that should be equal to some constant for all the frequencies. Now, this is interesting because the sum of the magnitude square response for all the filters, that should be a constant. Now, let us see what this would imply. Now, if you did basically decompose this modulus of h k e j omega square as some h k of e j omega times h k some conjugate of that, then this would be a constant. But if you carefully observe this transfer function, then you can see through inspection this is like my h k with f k, where h k is the analysis filter and f k is the synthesis filter, which is a conjugate of the analysis filter, right. So, from perfect reconstruction perspective, one can choose Fk of z to be Hk tilde of z, and of course you may question that the filters may not be causal. It is okay, but we can bring in some delay constraints to Hk tilde of z, and then the overall system could be, the output could be delayed, and therefore you are still bringing in the perfect reconstruction property here, right. So, the key question is, if I have designed tools that can give me filters that satisfy this power complementary property, then I am sort of home for good. Now, to just write it down carefully to ensure causality, one can impose delay constraints into Hk tilde of z, so that the output is delayed, and the delay would be reflected into a factor that would appear along with C. Okay, this is sort of straightforward. Now, let us look at the case for m equals 2, and C equals 1. This is power complementary case. Modulus of H1 of Ej omega square is 1 minus modulus H naught of Ej omega square. Therefore, H1 of Ej omega is a spectral factor of 1 minus modulus H naught of Ej omega square. That is, if you took 1 minus this magnitude square and then do spectral factorization, then you can get one of your filters as a spectral factor of this term. So, this is sort of straightforward. I will not be dealing with spectral factorization techniques, because this hopefully would be covered as part of your undergraduate digital signal processing. There is another special property which is all pass complementary property. So, filter responses are said to be, they are said to be all pass complementary if you take the summation of all the frequency responses over all the m filters, that should result in a transfer function which is essentially all pass, where A of z is an all pass filter. Now, you might wonder, is there any link with all pass complementary and strictly complementary function? Strictly complementary functions are all pass complementary because some gain times a delay is all pass, but all pass filters are not strictly complementary functions. Okay. Now, SC would imply all pass complementary, but not otherwise. Reverse direction perhaps not, is not implied. Now, but if you ensure that this is satisfied, we can at least guarantee that the reconstruction is free from amplitude distortion. Phase we may not be able to control here, but at least we can say that the magnitude response is unaltered, right. So, it is all pass. So, therefore, these are some basic properties. We have the last special property, which is doubly complementary filters. Filters satisfying both power complementary and all pass complementary or double complementary. So, it is double complementary if it satisfies both power complementary and all pass complementary. Now, this gives us a set of properties for constructing filters that are desirable. For example, if I say that, well, my unaliased distortion, my unaliased component of the overall system transfer function has to be doubly complementary, then it has to be both power complementary and all pass complementary, or I want it to be just strictly complementary, then I can imagine how I could build such filters, or I want it to be just power complementary filters, then I can say that, for example, for m equals 2 case, that the high pass filter is basically a spectral factor of 1 minus modulus of h naught of e j omega square, right. So, therefore, depending upon what constraints you want to bring in, you can essentially let the unaliased part of the distortion transfer function to satisfy one of these 4 properties, and once you are clear with that, then you can think about tools with further constraints on the filters and other properties of the special properties for these filters, if they have to be FIR or mirror symmetric, etc., so that you can realize practical filters. Okay. So, I think with this we are done with module 2, which is multi-rate systems and filter banks. So, this will give you an idea as to first how to go about constructing filter banks with the multi-rate operations, analysis towards getting the distortion transfer function, seeing through carefully how you would want to avoid aliasing errors, amplitude distortion, phase distortion, etc., and some of these special filters and their properties that you have can come handy if you want the response to be flat, to be just 1 or some constant c, or with satisfying perfect reconstruction property with some delay and then some gain, etc. So, with this you can get an idea as to how you can go about designing these filters and possibly their translates. Okay. So, we come to the end of this, and our next module would be into transforms, where we will discuss with wavelets. We will continue our journey from multi-rate to wavelets, because wavelets and filter banks are connected. It is one topic, comprehensive topic. Then we will look into KL transforms, which are data dependent transforms, and we will look into special considerations in the Fourier series representation and some of the convergence aspects. Okay, we will stop here.